We're in Unit 7, Lesson 10 right now, and we're going to talk about the natural E. Natural E is a number that's irrational. It has a value. Its value is 2.71828, and it goes on and on and on. It's kind of like pi. Pi is a symbol for 3.14, on and on and on. Well, E is just a symbol that refers to this number. It was discovered by a man named Jacob Bernoulli in 1683, I believe, and nothing was really, he discovered it, but nothing was really done until a man named Euler came along in the mid-1700s and saw its value, and he began to make formulas with this letter. So he is the one that coined the name E. And if you're interested in the history and development of this, Euler is spelled E-U-L-E-R. You can Google that and find all kind of fascinating things about it. But for the scope that we're interested in, I just want you to know that E exists, and it is a number 2.71828. We write it in our functions like this. The base graph, the parent graph of e to the x power goes like this, and it shows growth. The inverse path goes like this, e to the negative x, and it shows decay. If you're interested in that, feel free to go to Desmos and graph all kinds of variations on that theme. Now, as far as calculator goes, most calculators have an E button on them somewhere. Here it is as a second function. So if I wanted to find e to the first power, you press your power, second, E, and you see that gives you the 2.71828. If you needed a higher exponent, you just enter that exponent. You may have a calculator like this that has a separate button for E and for e to a power. This button right here, if you press it twice, it gives you the E, and you can see if I press enter, I'm going to get that 2.718 value. Then, if I need an exponent, I have this button up here, e to the block. Let's say I want to find e to the fifth power. Press the button, press the exponent, and then press enter, and it raises the irrational number e to that power. So now that we know what E is, let's look at what it has to do with logarithms and exponential functions. It's very closely tied into that. Just like log base 10 can be written log, we understand that's what it means. Log of base E became so common that they invented a new symbol for it, ln. If you look on your calculator, usually somewhere around the logarithm button, there is an ln button. This means log of base E. So if you see ln, that's what it's referring to, a log of base 2 point, on and on and on. Please note this is an ln, not a 1n. Okay, ln. And as far as any new material, that's all of it. So now we're going to take the E and we are going to combine it with some exponential functions and some logarithmic functions, and you're going to see all those properties that we've learned in this unit, they apply to the base E as well. So this will be a good review of those properties, and you'll get to use the new E. So first, let's just look at a couple of conversion problems. We're going to convert these two exponential equations into logarithmic form, and we're going to use that old property that we learned at the very beginning of the unit. Since a to the x power equals b can be converted to logarithm by saying log base a of b equals x, let's go over here and convert. Well, e is my base, so I'm going to have log base e, I'm going to swing around to 24, equals my exponent x. Only one more step this time, because log e, we're going to write that as ln 24 equals x. Okay, over here, same thing. Log base e of 72 equals x plus 5. So this would be ln 72 equals x plus 5. Now let's convert the other way. We have log form and we're going to go to exponential. We're still going to use that same property. Now, here we have ln x is equal to 58. So the first thing we're going to do is convert natural log to log base e of x equals 58. Then we can use our property. Your base, swing around here, this becomes your exponent equals your argument. All right, over here, same thing. We're going to convert natural log to log base e of x minus 9 equals 32. Then e becomes your base. Swing around here to get your exponent equals x minus 9. No solving, just converting. We're going to condense these into a single logarithm, and we're going to use those logarithm properties that we've already learned. When you have a sum of two logarithms, what did we do? This was called the product property, and it says if you have, and they have the same bases, both of these are log base e's. So all we have to do is multiply those arguments together, and we get ln of 48. Next, let's look at this one. It's a little more complicated. Let's condense each part of it first. So 1/3 times natural log 64. Have a number multiplied by your log, you can make it your exponent. So now what I have is ln 64 to the 1/3 plus ln x squared. This can be reduced to, what is the cube root of 64? ln 4. I'm not going to change anything here. Then we're back to using our product property again. Since we have a sum, this is going to be ln of 4 times x squared. And that's all you have to do to condense. It's the same thing, it's just that instead of log, you have ln. Now we're going to go backwards, and we're going to take these expressions and we're going to expand them back out. So the first one, I have a product here. I can send that backwards and make it a sum. So this is going to be ln 5 plus ln x, expanded form. All right, now here I have a fraction inside parentheses with an exponent, so I'm going to simplify that first. So this is going to be a to the 6th power, b to the 2nd power. Now I have a difference, so I can use my quotient property, and that's going to be ln a to the 6th minus ln b to the 2nd. Now I can use my property product to expand this even more and bring my exponent in front to be a factor. So I have 6 times ln of a minus 2 times ln of b. That's as expanded as it'll get. Okay, also here, simplification needed because my variables are combined under this radical sign, so I need to split them up. Alright, what I'm going to do here is, you know that your index on a radical can be combined with the exponent of your radicand to be a fractional exponent. So I'm going to rewrite this as m to the 2/3 power and n to the 1/3 power. That's how you undo a cube root. Okay, now these are multiplied together, so what I can do is use my product property and turn these into a sum. So I'm going to have ln of m to the 2/3 plus ln of n to the 1/3, and there's still some more expansion. Since this has an exponent, I can use my power property to make that a coefficient. So my final answer is going to be 2/3 times ln of m plus 1/3 ln of n. And that's how you expand natural logs. Now what we've been waiting for, we're going to solve equations, and we're going to check for extraneous solutions. So I'm going to work quite a few examples so you can see how similar they are to what we did with logarithms, so feel free to check out at any time and go work on your own problems. This is natural log 4x minus 27 equals natural log 15 minus 2x. Since we have single log, we can use the one-to-one property just like we did, And we can restate this as 4x minus 27 equals 15 minus 2x. Simple linear equation now. Let's add 2x to each side. So I get 6x minus 27 is equal to 15. Then we'll add 27 to each side. So I have 6x is equal to 42. Divide both sides by 6. And x is equal to 7. Now let's check to be sure this is not extraneous. If I put 7 in here, 4 times 7 is 28, minus 27 is 1. And if I put 7 here, 2 times 7 is 14, 15 minus 14 is 1. The statement is true, there are no negatives in my logs, so 7 is the correct answer. In this example, I've got 2 times natural log of x is equal to natural log of 2x plus 15. So the first thing I need to do is condense each side if it's not condensed fully. Here I've got this number multiplied outside, so I'm going to use my product property, and that's going to let me restate this as natural log of x squared. This side is condensed as much as possible, so I'm not changing it. Now that we have single log equals to single log, you can use your one-to-one property and state that, okay, x squared is equal to 2x plus 15. Now that's all the logarithm property, but what you have here is a quadratic equation. So if you're foggy on how to solve quadratic equations, I'll drop a link down in the description so you can review that section. But what we're going to do is get a 0 over here. I'm going to subtract 2x and 15 from each side. So now that's going to give me x squared minus 2x minus 15 is equal to 0, standard form. Then how do you solve quadratic equation? Well, we're going to have to factor the trinomial over here, and this will factor into two binomials. I'm going to use the zero product property. So since I have minus here, I'm going to have x and x, plus and minus. Need a pair of numbers that will multiply to give me negative 15 and add up to give me negative 2. So that's going to be a negative 5 and a positive 3. Then you set each side equal to 0 and solve. So I have x is equal to negative 3 or x is equal to 5. Now, I do need to check them for extraneous roots. So if I take negative 3 back up here and fill it in for x, right off the bat, I have natural log of negative 3. And that is not allowed. That negative number is not in the domain of logs. So I can cross it out. It is an extraneous solution. Now let's check the 5. If I put 5 in here, that's fine. If I put 5 in here, 2 times 5 is 10, plus 15 is 25. And if I wanted to check it, I've got 2 ln 5 is equal to ln of, we said 2 times 5 is going to be 25. Well, you use your product property here, so now you have ln of 5 squared is equal to ln 25. And ln of 25 is equal to ln 25. So here's our next problem. Natural log 72 minus natural log 4 equals natural log 6 plus natural log x minus 2. As with logarithms, my first job is going to be to condense each side as much as possible. So let's just focus on this side first. I have a difference, so I can use my quotient property, and that will let me condense this to 72 over 4, which will simplify down to 18. Alright, now over here I have a sum, so I can use my product property, and that product property tells me that ln of 6 times x minus 2 is equivalent to that. Then I can distribute this and get ln of 6x minus 12. Now that I have log to log, I can use my one-to-one, and I'll have 18 is equal to 6x minus 12. A simple linear equation, add 12 to each side, and 30 is equal to 6x. Divide both sides by 6. X is equal to 5. Now let's fill this in and make sure that we do not have an extraneous solution. If I put 5 in for x, I get a 3. So simplifying out, since I have this simplified to 72 over 4, is this equal to 6 times 3? This is a sum, this is a difference. That's why I'm dividing on this side and multiplying on this side. So I have 18 is equal to 18, and it checks. Okay, in this problem we have e to the x power equals 57. Remember, e is a number. Like pi, it's a number, and this is a variable exponent. So we have an exponential form that I can't easily solve. Our go-to here is to change it to logarithms. So let's convert this to a logarithm first of all. E is my base, so this is going to be log base e, remember swing over here, of 57 equals x. Now, what is log base e? Well, that is natural log 57 equals x. Now that you have a problem in this format where your variable is all by itself and this has a value, you can punch that into your calculator real quick. Natural log 57 is equal to 4.0431. Okay? And one last problem here. 5e to the 4x is equal to 95. I see that I have an exponential problem. How do I know that? Well, I have a base that's a number and I have an exponent that has a variable in it. When you see that variable exponent, that is going to be an exponential, and your best bet, unless you can do a one-to-one, is to convert this to logarithms. Now, before you convert it to logarithms, simplify it as much as possible. You want the exponential part to be all by itself. I can get rid of the 5. 5 is multiplied times whatever this is, so I can divide it on both sides. Now I have e to the 4x is equal to 19. Now convert to logs. This is going to be log, alright, what's your base? E. Swing over here and get that 19 argument, and then come over here, your exponent becomes the other side of your equation. Okay? Log base e is ln of 19 equals 4x. ln 19 is a number, so I can use my calculator, ln 19, and I can get 2.9444, that's plenty. It goes on out, but that's plenty, equals 4x. Divide both sides by 4, and x is equal to 0.7361. Okay? And that is all there is, except you need to practice now. Remember, it's very easy when I'm doing it, but you get some problems now and you practice, practice, practice. I'll see you next time.